Okay, this is the explanation for the multiple choice section. Starting with number one, the figure, as you can see here, shows a rectangular brass plate at 0 degrees Celsius in which there is a cut of a rectangular dimension as indicated, and the dimensions respectively is this one is y, the length of this is y, this one is x, this is larger than y as you can see, and this portion here is simply z. Now if the temperature is raised, so the thing that you have to consider is the term it's raised to 150 degrees, so there is an increase in the temperature. So which of these statement will be true? Now one of the things that you have to consider is this is a brass plate, and brass is a metal, as you know, right? So another thing that I want you to recall is the linear expansion, because this will be a case of expansion because there is an increase in temp of a metal happens, or it this happens equally in all linear dimension. If you can remember, if we have a circular let's say a circular ring with a hole, what happens after heating this one is the hole as well as the outer ring will simply expand without being obliterated to be an oblong in shape, right? So that means to say all of these dimensions expands equally. And that's also the same thing that is being applied here in this specific case. So I'm just going to equally in all linear dimension. So if you're going to check your choices, choice number one is saying that the dimension x will increase but the dimension y will decrease is clearly a violation of this statement. Therefore, that cannot be the answer. Both x and y will decrease. Yeah, that might be correct if it's the temperature goes lower than 0, but clearly that's not the case. So this is not a contraction but an expansion. For option C, x will decrease but y will increase is again a violation of this statement here, so that cannot be the answer. E, the change in x though depends on the dimension of z, that is generally not true. So the answer for this is both x and y will increase in the same rate, because as I've said, the linear expansion of a metal occurs equally in all linear dimensions. For number 2, which of the following statement is true? So basically, we just have to do a quick review on how we get the temperature scales conversion. So if you take the ratio of the Fahrenheit with respect to the centigrade or Celsius, the boiling point of water at Fahrenheit is 212. The freezing is at 32, and of course in the Celsius that is 100. If you take the ratio of that, I think you end up with 212 minus 32. Let me just quickly calculate that one. That's 180, and over 100. So that's your 1.8 or 9 over 5. So this is telling me that temperature of the Fahrenheit over T Celsius is simply 9 over 5, the ratio. Or the T Fahrenheit is 9 over 5 of temperature in Celsius. But I always have to remember that if I'm taking the reading in Fahrenheit, the 0 in Fahrenheit is already 32. It already has a 32. So that means to say I have to add here 32. Okay, so basically this is just one of the conversion factor. Then from here you can just take Celsius to Fahrenheit and vice versa. Another thing is the temperature in Kelvin. If you can recall this one, the temperature in Kelvin is simply the temperature in Celsius, and you add 273.15. Now let's try to investigate each of these statements one by one. So the first statement is temperature differing by 25 on the Fahrenheit scale must differ by 45 degrees on the centigrade or Celsius scale. So how do we do that? So firstly, this one is we take the change in the temperature in the Fahrenheit is equal to the change in this term EC plus 32. Now if we're gonna distribute the change class, this will result to the change in the temperature in the Fahrenheit is equal to, you take the constant out, 9 over 5 change of the temperature in Celsius. And you have to remember, or maybe one of the things that you have to think about is, if you're taking the change of a constant, in this case 32, that's just 0, because the change of a constant is 0, because that's a constant, it doesn't change, right? So this is 0, and this one you just distributed it right there. So from this statement class, you can check the statement number 1 if that's correct. So statement number 1 is saying na if you have a change in Fahrenheit, so 25 is equal to 1.8 or 9 over 5 of TC. So temperature on Fahrenheit scale now by 25 na change must differ by 45 on the Celsius. So that means to say, if that is a correct statement, this must be satisfied. However, a quick calculation will tell you that that is clearly not equal. 25 is not equal to 9 over 5 of 45. So this is not a correct statement. Now, B is quite confusing for some if you have not understood this principle. The change in the temperature of the centigrade or Celsius scale is equal to the change on the temperature on the Kelvin scale. So this is the principle that is correct. It does not say that the Celsius reading is equal to the Kelvin reading. Rather, it says that the change in the Celsius reading is just equal to the change in the Kelvin reading. So this one might look like correct, but this is not correct. 40 Kelvin corresponds to negative 40 degrees Celsius is not correct. Another way of thinking about it is simply looking at the conversion factor. So there is no way that when you plug in this will become 40K and then negative 40, that this will be satisfied. So that's clearly an incorrect statement. Let's go to letter E, because I think most of the students would answer E, but I will tell you straightforward that E is not the correct answer. Kasi this could have been correct if only it is written like this: 0 degrees Celsius corresponds to 32 degrees Fahrenheit. But if you're not really thinking about this statement, then you might be tempted to take this as your correct answer. Now, letter D is also incorrect. You can simply check it using this one, and you can see that it's not correct. What is correct is option C. Now, option C, you have to use this one. The change in TF is 9 over 5 or 1.8 of TC. That can easily be shown here. So, let me just write this one. The change in the Fahrenheit, 9 over 5 is just 1.8 of the change in the centigrade or Celsius. Now, it says here that the temperature difference of 10 degrees Celsius, so 1.8, delta TC is 10, must differ by 18 on the Fahrenheit scale. So the TF also must be 18. Now, clearly, that is a correct statement as it satisfies this equation over here. So the answer is truly C. Now for number 3, take the mechanical equivalent of heat as 4 joules per calorie, and then you have a 10-gram bullet moving at 2,000 meters per second. So if we have a bullet here, the mass of that bullet is 10 grams, and then it's moving to the right with a velocity of 2,000 meters per second. And then it's mentioned here it plunges into a paraffin wax that has a mass of 1 kilogram, and then initially it has an initial temp at 20 degrees Celsius. Now, according to the problem, you assume that all the bullet's energy heats the wax, and what will be the final temperature of the paraffin. Now, in this case, you have to understand that all the energy of the bullet is in the form of kinetic energy, right? Because it's the energy associated with the motion of the bullet. Now this one here, if it has to increase its temperature to some reading degree Celsius, then it needs an energy also in the form of heat. So what happens here is the kinetic energy of the bullet, which is a form of energy, is converted into the heat energy that is used to melt the wax. So what I'm going to do is to simply have the Q of the bullet is just equal to the Q that is gained by your negative Q loss. It's still the negative Q loss plus Q gain. Negative Q gained by your paraffin. I'll just put P. And I'll just put B here for brevity. Now, I'm simply going to calculate the kinetic energy. Actually, I messed this up. It should be kinetic energy. Okay. I'm going to calculate the kinetic energy of the bullet, and if you can recall, that's just 1/2 mv squared. And substitute the mass is simply 10 gram or 0.01 kilograms. The velocity is 2,000 meters per second. So a quick check of the unit will tell me that I'm getting joules for the kinetic energy. So, but let's calculate that one. I have 1/2 multiplied by 0.01 multiplied by 2,000, that's square. So I have 20,000 joules. Okay, now that's joules, so I have to convert that into calories because as you can see, that will come in handy because of the fact that the C of the paraffin is in calories. Now I'm also given the conversion factor here for joules is 1 cal, or equivalently for joules is 1 calorie. Equivalently to 20,000 calories will reduce to 5,000. No, sorry, calories. It should be 5,000 calories. The joules cancel out in this case. Okay, so that means to say that the Q of the paraffin, which is just heat energy in this case, is mc delta T, right? I'm just gonna put P for the paraffin so that I won't be confused with the mass. I'm looking for the final temp. Now, this QP here is simply just the kinetic energy provided by your bullet, because after all, they are just energy, so they can be equated with each other. So let me just put this as KE is equal to MPC, so that the right hand side will be left with delta T. So if we will further expand this one, oh no, sorry, should be copy. We further expand this one, we have delta T is simply TF minus TI, right? So T final minus T initial. I'm looking for T final, so T final will just be kinetic energy divided by the mass of the paraffin, specific heat of the paraffin, plus the initial temp, which is 20 degrees Celsius. So I will let you do the calculation, but I'm just going to show the units for this case. So the kinetic energy in terms of calorie is just 5,000 calories. The mass of the paraffin in this case is 1,000 grams or 1 kilogram. And then the specific heat is 0.7. So you should be very careful with your units, because if you plug in the incorrect units, you'll get a number, but that's messed up number. So the initial temp is 20 degrees Celsius, so you get TF. Now, upon checking the units, that's why it's really important to always use the units as a way of checking your answers. So calories will cancel out, this one will cancel out, and 1 over C degree is equal to C, a degree Celsius. So degree Celsius plus degree Celsius, so you get the correct answer. And when you do the calculation, you should get 27.1 degrees Celsius. So the paraffin is heated to 27 degrees Celsius. And where does it get that heat energy? That's simply the heat energy, which is just the kinetic energy of your bullet moving at a very fast speed. Number 4, the mercury column in an ordinary medical thermometer doubles in length when its temperature changes from 95 degrees Fahrenheit to 105 degrees Fahrenheit. And then you have to choose the correct answer. So basically, all of these statements are asking for the coefficient of volume expansion. So we have to recall some principles in our discussion that beta, corresponding to the volume expansion coefficient, is generally 3 times the linear coefficient, which is alpha. Now, delta L, if you can recall, the change in length is equal to the initial length, the coefficient of linear expansion, delta T. So if I'm going to look for an expression of alpha, I'm simply going to divide both sides by L naught over delta T. So delta L over L naught delta T will give me alpha. Now, why did I solve it like this? Because I can actually solve for alpha in this case. Now, this term class delta L over L sub 0 will give me 2, because it's mentioned here that when there is this change in the temperature, the length doubles. So this term, as I've said, this term will result to 2, so that is just 2. And the delta L is the final temp is 105 minus 95, that will give you 10 Fahrenheit degree change, or 1 over, I don't know, 2 over 10 is 0.10, I guess. Let me just check. 2 divided by 10. Yeah, sorry, 0.2. So this will give me 0.2 per Fahrenheit degree. So we're now ready to check which statement fits what we had just calculated. The coefficient of volume expansion, so this is just your alpha, so beta will give you 3 times of 0.2 per Fahrenheit degree, or 0.6 per Fahrenheit degree. So upon checking, this statement number 1 is incorrect. Also, statement number 2, also statement number 3, or letter C, D is also incorrect. So the correct answer is ironically none of the above, because the beta here is 0.6 per Fahrenheit degree. Okay, for number 5. A balloon is filled with cold air and placed in a warm room. So to help us visualize, imagine this is your warm room. Okay, this is your warm room, and it is at temp of T sub H, a higher temp. And then you have here your balloon. The balloon is, of course, smaller compared to the room, but that's not the point. The point is the temperature of the balloon is cooler compared to the room. Now, you have to recall something about this one. If you can recall, PV is equal to nRT from your chemistry, just to provide with a solid mathematical explanation, that means to say that V is just equal to nR over P times T. Now this one is just a constant. These terms here are constant or fixed, so we'll just call this some alpha, so that we can have V is just equal to alpha times T. Now what this is telling us is that there is a direct proportionality between the volume and the temperature. Now notice that in order for the balloon to be in thermal equilibrium with the warm room, the surrounding air, this is telling us that T sub C at some point must approach to TH for it to be in thermal equilibrium. So that means to say now we have to change the temperature to higher values in order for it to be in thermal equilibrium with the room. And what's the consequence with the balloon? The balloon, since the temperature is directly related to the volume, will also expand in size or change its volume by increasing the volume. So the balloon is not in thermal equilibrium with the room until it's still expanding. So this is the correct answer, until it stops expanding. Kasi for it to be in thermal equilibrium with the room, for it to raise its temp to be equal to TH, the consequence is for it to expand its volume also. Number 6. Suppose object C is in thermal equilibrium with object A and B. The zeroth law of thermodynamics states. So if you can recall, this is how it was illustrated in the book. So C, and then you have here object A or system A, and then some system B over here. Now let's check which one of the statement is consistent with the zeroth law. It says here that C will always be in thermal equilibrium with both A and B, that C must transfer energy to both A and B, that A is in thermal equilibrium with B, that A cannot be in thermal equilibrium with B, nothing else. Okay, so basically this is a straightforward like definition of what the thermal equilibrium is, and that is when C is in thermal equilibrium in A, and of course C is interacting with B in the same rate, that means to say that in the same way, it means to say that A must also be in thermal equilibrium with B. So that is clearly the statement letter A, that C will always be in thermal equilibrium with both A and B. For the 7th question, you have 50 grams of ice at 0 degrees. So it would be very helpful if you can sketch this one. So we have a thermos bottle here. That's your thermos bottle. Of course, that's closed so that there's no exchange of energy outside. It contains 100 grams of water. So you have water, 100 grams. That's the mass of the water. And then you also have ice, right? 50 grams of ice. So let me just draw it like this. It should be floating, but yeah. So those ice there are 50 grams. That's the mass of the ice. M sub ice. Now basically the principle here is very simple also. The heat that is lost minus is equal to the heat that is gained. So this is just a very simple principle behind this. Now who gains the heat? Now take note that in this specific problem, it asks you of how many grams of ice will melt. And for melting to happen, the ice needs to gain heat. So this one is the ice. Another thing that you have to consider, class, is the ice here is already, about 50 grams of ice, it is already at 0 degrees Celsius. That means to say, the ice, this one, will gain the heat of the water, but it does not need it to change its temp for it to phase change kasi naka 0 degrees na siya. So that means to say the entire heat energy by the water, which is gained by the height, will be automatically used by the ice for phase change. And the one that is losing the heat is your water. Syempre because of the fact that your heat flows from high temp, T higher, to cooler temp. So that's why the one that is losing is obviously it's always the one with the higher temperature, in this case water. So if you have to calculate this one, of course you have to calculate this one. This is just gonna be, you can take it step by step. You take the Q of the water first. So Q of the water, it's just MC delta T. So you have the we're using joules. So 0.1 kilogram or 100 grams. Am I right? Let me just check. 100 divided by 1000, yeah, it's 0.1 kilograms or 100 grams. That's for the water. The specific heat of water is 4190 joules per kilogram. That Kelvin, or that is equivalent also to saying joules per kilogram, that C degree, because as I've said earlier, this is a change already. The change in Kelvin is equal to the change in Celsius. So for simplicity, I'm going to use the C degree because they are just practically the same. And then the change in temp, the final temp of your water is 0. I'm hoping you can imagine that from 6 it has to reach to 0 so that it can be a thermal equilibrium with the ice. Minus initial temp at 6. Okay, 6 degrees Celsius, so this will result to Celsius degree. So the Q of the water, if you will calculate that one, is equal to 0.1 times 4190 times 6, 2514. So you have 2514 joules. So that's the heat energy. This is actually negative, implying that this is the heat energy that is being lost by the water. And of course, by the conservation of energy, it cannot be lost just out of nowhere. It has to be gained by the other one. So this lost energy by the water is what is gained by your ice for it to melt. So simply, you have negative 2514 joules. I will let you do the calculation. That is equal to the Q, but this Q here is for the phase change. So since that is a phase change, that is just the mass of the ice. But take note, this is the mass of the ice that you are looking for. This is not this mass. Mass of the ice, just have mass of the ice, L, meaning lost, and then multiplied it by the latent heat of fusion, which is 334 times 10 to the 3. That's the kilo here, kilojoules per kilogram. So when you calculate this one, you will get to the conclusion that this amount of energy, heat energy, will result to the melting of this amount of ice, and you'll get 7.5 grams of ice that can be melted. Okay, so the next one is number 8. The same heat energy, okay, the same heat energy Q enters 5 different substances. Which substance has the greatest specific heat? So we always remember that if it has a greater specific heat, that means to say it will have a small change in temp per unit mass, right? It means to say, if, for example, let's just give an example, water and copper. For water, this is 4190 joules per kilogram, that's degree. For copper, if I can recall correctly, it's 390 joules per kilogram, that's C degree. This means that for water, it needs 4190 joules of heat energy for 1 kilogram of it to change the temp by 1 Celsius degree. For copper, you only need 390 joules of energy for 1 kilogram of it to change by 1 Celsius degree. So that means to say na if it has a greater specific heat, in this case water has a greater specific heat, it will have a small change in temp per given mass, or equivalently, it doesn't increase its temp that much directly. So that's why water is a good thermal regulator of the earth. So to answer this question, if you have understood that one, you will simply look at the changes in the temp. So if it has a great specific heat, then more likely or logically, it must have a small increase in temp. So 10 increases by 10, increases by 4. So of all of this one wins out. So kasi your 4 grams only increases by 4 Kelvin. So that means to say it's quite resistant to changing its temp, and that's probably attributed to the fact that it has a high na specific heat. Okay, so the answer for this is option B. Okay, for number 9, metal pipes used to carry water sometimes burst in winter. For what reason? I'm hoping you can remember about the discussion on the anomalous behavior of water. So we have here, it's graphed like this, or is presented like this, where the x-axis is your temperature in Celsius or centigrade, and then on the y-axis it is its volume. Now the graph looks like this one. Now there are specific points like 4 degrees Celsius, and it was mentioned, no, that's the densest temperature of your water, and the graph actually looks like this, like that, if you can remember. That means to say na your water at 4 degrees Celsius has the lowest possible volume. Now density, which is just the mass per volume, as a consequence, if you have the lowest possible value of volume at 4 degrees Celsius, so if the volume decreases, of course, conserving the mass, the density also increases. That's why we have the claim that water is densest at 4 degrees Celsius because it has the least volume possible. But that's not the point that we are trying to talk here. Now, from 4 degrees Celsius onwards, you see that an increase in the volume, so that's quite normal. However, if we look into the domain of the temperature 4 degrees Celsius to lower than that, to zero, for example, we're actually noticing a change in volume, and that's anomalous because we don't usually see any material so far in our discussion that increases in volume as the temperature drops. Kasi normally, if the temperature drops, it should shrink, the volume should decrease. So hence the term, the anomalous behavior of your water at this domain here. Now that explains why na your water, when it freezes, of course, at 0 degrees Celsius at 1 atmospheric pressure, it has the maximized volume because if you remember the simulation, the water would actually be building up uh, like crystal lattice like this one. So it has a large volume over there, and that actually can be seen from the graph. As it approaches 0, it approaches, it's an increasing trend in the volume. So that explains the question. So the metal pipes that carries water during winter, of course we don't have that in the Philippines, but you can imagine that if the temperature during winter, the temperature drops to below freezing, right? And freezing temp results to expanding volume. So that's why they burst, because of the fact that water must have expanded there. And the correct statement is ice expands when it melts. Is it correct? No. Water expands when it freezes. So that's why the metal pipes burst. Because as it approaches freezing temp, the volume of the water actually increases as it turns to ice. So, burst. Number 10, the diagram shows 4 thermometers. The freezing and the boiling points of water are indicated. You have to rank the temperatures according to the size of a degree on their scale from smallest to largest. Now, that means to say, class, Morabag, it's just like this. So if these are the range of the readings possible, what's the size of the degree? So if I'm going to divide each of this by, say, 10, going to create a thermometer na tag 10 ang grades kanang calibration bitaw niya mga lines, equivalent to 10 at 10 lang na siya tanan. So how large daw ang reading sa ako ang isa ka scale dito So of course, to solve this one, you simply take the range of the value. So this one is 100. 125 minus 45. Okay, 125 minus 45. I have to calculate this one. I'm too tired to think. It's 80, so the interval is 80. 175 minus 55 is 120. And then 75 minus 35 is 40. So the question is, we have to rank according to the size of a degree from the smallest to the largest. Now, if these are the intervals within the boiling and the freezing, 100, 80, 120, and 40, that means to say if I will equally divide all of this thermometer into simply 10, so that means to say nga si 40 naman yung interval here, i-divide na ko by 10, so each of the will be 4 degrees ang each kini siya nga part here, kini nga interval. That's 4. Now for 120, if i-divide na ko na siya by 10, each of this will result to 12, right? 12. And if divided by 10 is this is 8, and 10 this is 10. So basically ang pinakagamay og values kung i-divide og 10 kay kinig yung 40 nako. So 40 z sunod niya gamay is kanang 80 or x sunod niya kay si w nga 100 og si y, and that is your option D. Okay, so the problem solving will follow afterward.